This is a presentation from Integral Building on building science and engineering and sustainability. The topic is Beyond Current Code, using common sense and passive house energy modeling to reduce energy and create a more healthy, optimum environment. We'll be looking at a 3-story row house in San Francisco undergoing remodel and addition. Notice that this is situation where you have houses on both sides. You don't even have access to the exterior walls. And it's on a slab on the ground floor. This turns out to be important. So we have a comparison of the transmission and ventilation losses for a typical California construction if this house was done to barely meet code now. After applying common sense, basically increasing the insulation and reducing the leakiness of the house, we get a big improvement. When we further apply passive house energy modeling, quantitative energy modeling, using some of the scientific tools, we get even more improvement. Here, comparing common sense and typical California construction. When the biggest change is by insulating under the slab. Another big change is when we go from a leaky house, 8 air changes per hour at 50 Pascal with no heat recovery ventilation, to a fairly tight house, 2 air changes per hour at 50 Pascal with heat recovery ventilation. We also get improvements when we increase the insulation in the walls, primarily by increasing the insulation in the new walls of the addition. If we compare passive house, the PHBP energy modeling results and our common sense approach, if we increase the air tightness further from 2 air changes per hour to 1 air change per hour, notice it's not a big difference. If we improve the windows, and we'll see more about that, that we also get some improvement. But the real improvement here is when we get rid of the thermal bridges and when we insulate the one wall which was thought not worth bothering with because it was too hard to get to, it had wood paneling, too much trouble. The windows, if we have double pane windows with the typical low gain glass that reduces the chance of overheating, but it also reduces the amount of solar heat that comes into the house. Basically, we have about twice the losses through those windows over the course of the year compared to the gains we get through those windows. If we go to triple pane windows and we have the high gain glass, clearer glass, glass that has an appreciably less tint, we see, amazingly, slightly more energy coming in through those windows over the course of the year than is lost. Let's look at what we mean by these thermal bridges. Ideally, where we have a change in geometry, we have a constant temperature on the inside of the building. Okay, and these are the colors. And that constant color there means we have constant temperature. This is how it ought to be. But this is a thermal bridge. Here we see the slab there's insulated under the slab. The wall is insulated, but this slab is connected monolithically with the foundation, the ground, and the outside. We see that the temperature of the slab in the middle is room temperature. The wall is room temperature. But toward that corner, under severe conditions, the temperature can go down, way down. We can actually put a number to this effect. This is 0.638 BTUs per hour per foot along the length per degree Fahrenheit. Less than 1 BTU, it's not a big deal, yeah? times 13 degrees, the difference between the inside and the outside, times 365 days, times 24 hours, is 8 million BTUs, or 80 therms. Similarly, where we have a retaining wall and we have the slab connected monolithically, we have this poor result. And where we have a post coming down, we stop typically, structural engineers would expect to stop the insulation and have a 2x2 or a 3x3 area where the interior slab is connected directly to the ground. Those are all thermal bridges. So if we get rid of these thermal bridges, how do we do this? We run the insulation under the slab and right and up to the corner, up to the wall. This is a different color because it's a denser insulation, just in case here in seismic California we have some pushing, some slamming against that location. Here we see that the inside of the slab all the way to the corner, same as the wall, is all one temperature. Similarly, we run the insulation up. We can even have a nailer. We can put a nailer here. This is a practical solution. And we see that the inside temperature is constant. The thermal bridge calculation, it comes out to be negative. If we neglected and said, we're just going to consider that we don't have a thermal bridge here, we're going to just use our simple results from the area calculations, we would be conservative. Underneath that post, we can put foam glass, say a 1 foot by 12 inch by 12 inch square that can take almost 13,000 pounds per square foot, ultimate. If we use a safety factor 2, that's 6,500 pounds. Okay, if we have more than that, we can essentially thicken this slab to spread the load more. But the foam glass, in addition to being so strong, has about the same insulative properties as styrofoam, as insulative foam. So, by going from typical California construction to using common sense and passive house energy modeling, we reduce the peak heating load, for instance, by over 75%. We get rid of the forced air furnace using a hot water heater to supply both domestic hot water and space heat. We get rid of the dusty, dirty ducts, 8-inch ducts leading to registers in every room. Instead, we have 4-inch ducts supplying fresh air and most of the space heat. And this is filtered fresh air. We increase the comfort because there's not cold surfaces around us. The more even the temperature of the surfaces around us, the lower the air temperature can be for the same comfort. And over the course of 50 years, we can reduce the carbon dioxide generated from 429 tons of carbon dioxide to 67 tons. Thanks.